A very good day to Dr. Muhammad Hairunizam and Madam Shahar Azalia. My name is Bartolomeo Nakdilor from 4BKG Section 1. I'm going to present my research about the development of rotational to linear actuator being supervised by Professor Madya Dr. Kasrul. Before we go into the introduction, this is a basic concept of rotational to linear actuator based on ball screw mechanism. My slides contains 6 major topics, which are: first, the introduction; second, the problem statement; third, the objectives; fourth, the scope of research; fifth is the methodology; and lastly is the conclusions. Towards academic excellence. This is our motto for Faculty of Electrical Engineering. For the introduction, rotary to linear actuator typically operate by conversion of rotary motion into linear motion. This conversion is commonly made via combination of electrical motor and mechanical mechanism. In this research, the prototype of rotary linear actuator based on roller machine is proposed. The problem statement encountered in this research is that most of rotary linear actuator utilize ball screw mechanism. This actuator have an electric motor with set of gears to drive the ball screw mechanism. Thus, it has rather complex fabrication. As shown in the figure, depending upon their lead angle, the ball screw can be back-driven due to their low internal friction. For example, the screw shaft can be driven linearly to rotate the ball nut. In this research, we focus on 3 main objectives. First is to design rotary linear actuator based on rolling disc principle as in roller bender. Second is to propose new structure of utilized rolling disc driven by DC motor. And last is to build a suitable DC motor controller in terms of speed and direction. In this scope of research, the project's purpose is to develop a new function within the organization. The CAD modeling of the rotary linear actuator based on bending machine is done using SolidWorks. The directional of DC motor is done using a microcontroller. The design is based on the idea of 3 rolling discs on a small scale. The first rotary linear study is about the rotary linear switch reluctance machine. In this research, the rotor has a degree of freedom in rotary and Z directions. The overall cost of motor is minimal since no expensive components are needed. Some basic criteria for practical applications, such as the high temperature operating environment, can be satisfied by using this type of motor. The gain is that the individual mover slot with coils amplifies the winding system, thus reducing the production cost of moving board. Zero inductance between opposing movers with flux decoupled windings can be achieved, and long distance travel can easily done by combining longitudinal monitoring support. The next study is about the low complexity rotary linear motor. The machine stator has a glossy hollow cylindrical form and consists of 2 separate components, each with ferromagnetic core and a winding. The winding of each module, whose active sites are eventually located within the slots, features a symmetrical 3-phase structure. Gains of the study is it is presumed that the stubble frame encloses the stator modules and the mechanical shaft supports the active sections of the mover. Each stator module essentially has the same form of structure as the typical stator for brushless synchronous or inductive machines. The next study is about the rotary linear motor composed of 4 primaries with independently energized ring windings. In this research, the machine has a short plural key linear induction motors, LIMS. Independently energized double layer ring windings were adopted for each main. The remarks is that by using the ring winding instead of the nominal drum one, space between the opposing primaries is reduced and adequate rotary force can be produced. Each primary winding is energized by multi-phase supply with independent phase shifter, and the cylindrical secondary solid conductor is separated from its back iron. Operation of the secondary conductor is possible in any 4 quadrants of the linear rotary plan. Finally, the last study is about the rotary linear induction motors. The motor stator is composed of 2 windings. Changing the supply voltage or frequency will affect the rotor's motion, thus changing the direction and the value of the rotor's velocity. The 2 fields acting on the common rotor led to the rise of 2 forces, linear and rotary. What we gain from this study is that motor consisting of 3-phase magnetic field generating stators, where the field axes of the opposing stators are rotated at certain angle. Double primary motors, where one primary is a stator connected in tandem, which produces a translator motion. Motors with single helical wound primary stack. Double winding motors, where the primary laminated stack has 2 independent windings to produce the rotating and traveling fields. Now let's go into the methodology. First is the research about rotary linear actuator based on roller bender and suitable control circuit for rotation of DC motor. Next, we do data study about the N555 motor PWM with forward and reverse circuit. After that, we do analysis on the simulation of mechanical part and the electrical part. Finally, we do the comparison results taken from simulation. Now we will look into the research flowchart. The first process is to do research on rotary linear motion. Next process is to design rotary linear actuator based on rolling disc principle. The third process is to propose new structure of utilized rolling disc driven by DC motor using SolidWorks. The fourth process is to study the suitable motor controller for speed and direction. Now the decision making is whether the DC motor can be controlled both speed and direction. If yes, we analyze data taken from Proteus and start writing a thesis. If no, we go back to study the suitable motor controller for speed and direction. This is a process of rotary to linear motion. It is a slider crank mechanism. It is extremely cost-effective means of converting rotary to linear motion. The crank portion is the wheel that rotates about its center and has a rod of fixed length mounted to a point on its circumference. The other end of the connecting rod is attached to a linear stage which is constrained to move in only one dimension on a relatively frictionless surface. At both its location, the connecting rod is free to rotate, hence the angle formed with horizontal will change as a function of the disc position. As the disc travels from 0 to 180 degrees in the counterclockwise direction, the linear stage moves a distance equals to 2 radius. If the disc continues to travel from 180 degrees to 0, still in the counterclockwise direction, load will move in opposite direction over exactly the same linear distance. This is the prototype design of a rotary linear actuator based on rolling disc principle of a roller bender. It has the electrical motor and mechanical mechanism to define the concept of rotary to linear conversion. The CAD modeling of the bending machine is built using SolidWorks. This is the mechanical parts of the bending machine. This is a DC motor controller which I designed. It has 4 major components. The first one is the NE555 IC timer, the 100K potentiometer, the DC motor, and lastly the 9V DC power supply. This is the PCB layout that I've designed in Proteus. J2 is the 9V battery, P1 is the potentiometer, J1 is the DC motor, J4 and J3 is the 6-pin push button switch. All are represented as terminal blocks. R2, R3, R1 are the resistor, whereas the D2, D1 are the diodes. And U1, U2 is the microprocessor, and C1 is the capacitor. Next, for the preliminary results, I will show the simulation in Proteus. This is the simulation I will do in Proteus. The 9V battery, the resistor, switch, LED, microprocessor, and the DC motor, and the potentiometer. And we use oscilloscope to get the output waveform. Now we turn on the switch. As you can see, the DC motor starts to move in clockwise direction and at duty cycle of 50%. Now we try to increase as the speed of the motor increases. We increase the duty cycle to change the speed and the direction of the DC motor. The potentiometer is set at 89% duty cycle. Now we can see we set maximum duty cycle of 100%. The motor speeds increase. We lower down the duty cycle to 32%. The DC motor moves counterclockwise, which is in reverse motoring in the third quadrant, where they have negative torque, negative speed, but still power dissipated is still in positive value. For future works in FYP2, we will fabricate the actual prototype, add limit switch to control the limit of extended range, and lastly to improve compact design in terms of size and thrust force, where we need small motor at high torque. Before we end the slide presentation, we go into the conclusions. The first conclusion is that we had covered the design of rotary linear prototype, simulation, and practical implementation of a low-cost bidirectional speed control of DC motor. Secondly, the proposed control system model can control the DC motor speed and direction by varying the duty cycle of the output PWM signals. And lastly, the E555 IC timer can integrate all required functions in its single chip, and therefore it reduces the hardware setup of the overall control system. A very good agreement was achieved between the experimental and simulation results. This is the references cited in the summary of literature review.